Welcome to Electronic Seed YouTube channel. Today in this video, we will learn about the fundamentals of digital signals. Let's get started. I will walk you through the fundamentals of digital signals. We will look at what they are and how they differ from discrete-time signals. Then why we need them, with real examples like temperature and voltage. And remember, increasing the number of quantization levels reduces the error. If we already have analog and discrete-time signals, why go digital? Digital signals allow robust storage, processing, and transmission without degradation. Analog systems tend to accumulate noise and suffer from component tolerances. Digital systems can regenerate exact levels at each step. Think of music on a CD. It sounds the same every time, while a cassette tape wears out. So the need for digital arises from noise immunity and reproducibility. Discrete-time signals mean only time is sampled at equal intervals. But the magnitude, or amplitude, can still take any continuous value. Digital signals force the magnitude to take only specific allowed levels. So both axes become discrete, time and magnitude. We divide the time axis into equal segments, t0, t1, t2, and so on up to tn. The constant interval delta t equals t1 minus t0, which equals t2 minus t1, and so on. So far, this is no different from discrete-time sampling. The new step is the quantization of the magnitude axis. Consider a temperature range from 0 to 100 degrees Celsius. We start with just 4 levels, 0, 25, 50, 75, and 100 degrees. At time t1, the actual temperature is 22 degrees. The lower level, or floor, is 0 degrees. At time t2, actual is 48 degrees. The lower level is 25 degrees. At time t3, actual is 74 degrees. The lower level is 50 degrees. At time t4, actual is 100 degrees. It falls exactly on a level, so we quantize to 100 degrees. At time t5, actual is 1 degree. The lower level is 0 degrees. So the signal can only take on the preset levels we chose. The error is the difference between the actual value and the quantized value. Imagine a voltage range from 0 to 5 volts. First, we use only 2 levels, 0 volts and 5 volts. At time t sub, the actual voltage is 2.2 volts. The lower level is 0 volts, so the error is 2.2 volts. Now increase to 5 levels. Step size is 1 volt, so allowed values are 0, 1, 2, 3, 4, and 5 volts. The same 2.2 volts falls between 2 and 3 volts, so the lower level is 2 volts. The error is now only 0.2 volts, which is much smaller. With 11 levels, we have 0, 0.5, 1, 1.5, and so on up to 5 volts. 2.2 volts lies between 2 and 2.5 volts, so the lower level is 2 volts, and the error stays 0.2 volts. To represent 2.2 volts exactly, we would need infinite levels, which returns us to a continuous signal. In practice, 8-bit quantization gives us 256 levels, which is a good compromise. The key takeaway: more levels lead to a smaller quantization error. Take an audio recording example. We sample every 0.1 milliseconds. A discrete-time signal would let each sample have any amplitude, like 0.12345677 volts. That would require infinite precision for storage, which is impossible. A digital signal rounds each sample to the nearest allowed level, for example using 65,536 levels with 16 bits. Thus, each sample is represented by a fixed number of bits. First, choose the sampling interval delta t, which is determined by the Nyquist frequency. Second, choose the number of quantization levels L, which affects dynamic range and error. The quantization error is less than or equal to the step size Q when we use floor quantization. If step size equals Q, then the maximum error is Q. Floor quantization gives an error between 0 and Q. Rounding gives a symmetric error, but the principle is the same. So more levels mean a smaller Q, which means a smaller error. Digital signals require equal time intervals and fixed magnitude levels. Using lower-level floor quantization minimizes error in my scheme. Increasing the number of levels improves accuracy. Analog signals can be more accurate since they have infinite levels, but digital offers several advantages. Repeatability, error correction, easy processing. In our next post, we will look at concrete examples of analog to digital success stories. Can you think of a real-world device that still uses pure analog signals? Why hasn't it gone digital? Post your answer in the comments below.